Good afternoon, everyone. Thanks so much for coming to our MIT Manufacturing Distinguished Speaker Series, where we have the great honor of hosting the CEO of Intel Corporation, Pat Gelsinger. And the format of the hour will be a conversation on the future of semiconductor manufacturing. So to make formal introductions, please welcome Professor Anantha Chandrakasan, Dean of the MIT School of Engineering.
Thank you, John, and good afternoon, everyone. I'm delighted to be here today to welcome Pat Gelsinger, the CEO of Intel, to MIT. He started at Intel in 1979 as a teenager and eventually became the company's first chief technology officer. During this time at Intel, he was behind key technologies we're familiar with today, including the original 8486 processor. His work helped Intel become the world's preeminent microprocessor manufacturer. In 2009, he became president and chief operating officer of EMC, where he was responsible for storage, backup, and data computing products. In 2012, he became CEO of VMware, a leader in cloud infrastructure, enterprise mobility, and cybersecurity. He rejoined Intel in 2021 as CEO and almost 1 year after the start of the pandemic. In his role as CEO, he leads more than 130,000 employees across 46 countries. He's committed to significantly expanding semiconductor manufacturing in the US. Intel is adding 2 fabrication facilities to its Phoenix complex and opening a new facility in Columbus, Ohio. He's focused on making the company the leader in chip manufacturing and packaging and revitalizing the semiconductor industry in America. He's been in close touch with Washington, D.C., and has strongly supported and driven the CHIPS Act. He holds engineering degrees from both Santa Clara University and Stanford University. In 2019, he was ranked the top CEO in America in Glassdoor's annual employee survey, and just last month, he was elected to the National Academy of Engineering. Please join me in giving Pat a warm welcome. I would also like to welcome our other distinguished panelists, Professor Daniela Rus, who is the Andrew and Erna Viterbi Professor of Electrical Engineering and Computer Science, and the Director of the Computer Science and Artificial Intelligence Laboratory. Professor Vladimir Bulovich, the Fariborz Massey Professor in Emerging Technology and the Director of MIT Nano, and Professor Jesus del Alamo, who is the Donner Professor and is Professor of Electrical Engineering in the Department of Professor of Electrical Engineering in the Department of Electrical Engineering and Computer Science. So please join me in welcoming our panelists, and now I pass it over to Jesus.
Welcome. All right, thank you, Anantha. Welcome, everybody. Pat, welcome. It's a real treat to have you here today for this conversation. So we have a few questions for you, and maybe the first one should really be about a much commented issue, the end of Moore's Law, which has been in the media for far too long. And in spite of all this, the semiconductor industry keeps making tremendous progress for years. So still the question is, how far can we go? At some point, integrating more transistors might not be economically advantageous. So how will this industry continue to increase the power of electronics beyond that point when making more transistors is not worthwhile?
Yeah, and a few thoughts on this. Number one is I think we've been declaring the death of Moore's Law for about 3 to 4 decades. Yeah. Right, and it's one of those. It's like rumors of my death are highly exaggerated, and to some degree, we have about a decade of visibility in front of us. Mm-hmm. And when we've gone 3 or 4 years into the future, we have about a decade of visibility in front of us, right? So, it's like, we keep solving problems that allow us to keep rolling forward about a decade in front of us, right? And, that's the way it's been. Now, fundamentally, we had what we called the Dennard era of Moore's Law, where essentially you were just able to shrink in the XY, right? And being able to do 0.7x shrinks in the X and the Y, right? You're able to get this doubling every 2 years approximately. And that was like the golden era of Moore's Law. We're no longer in the golden era of Moore's Law. It's much, much harder now. So we're probably doubling effectively, closer to every 3 years now. So we've definitely seen a slowing. We've seen a shift in the economics associated with Moore's Law. A modern fab, 7, 8 years ago would have cost about $10 billion. Now it costs about $20 billion, right? So you've seen a different shift in the economics. But here we are today, and the most advanced chip that we build today is about 100 billion transistors, right, on a single package. Well, that's a lot of transistors. Now, where we are today, we believe that 4 major things are allowing us to get to 1 trillion transistors by the end of the decade, which is approximately a doubling every 2 years. And with that, one is we have a new transistor type, right? We're going to this gate-all-around, so we've solved the transistor problem, right? We have a new power delivery mechanism. We call it ribbon-fed, essentially creating a wafer sandwich, putting power delivery from the backside as opposed to the top side, so you solve a lot of power, droop, delivery, density issues by doing that. So number 2. Number 3, lithography. Lithography has been the heart of semiconductors ever, right, for it. And with EUV, right, extreme ultraviolet, essentially using X-ray, we went from 193 nanometer light down to 13.5 nanometers, right? So you saw a dramatic, right, decrease, right? It took 20 plus years and was a decade late, but that is now solved. And we have the next generation of that called high numerical aperture lithography, right? Which will have the first machine in our Oregon facility by the end of this year. Yeah, first one on the planet, right, outside of Europe. So lithography is solved. But number 4 is that chips themselves are going from being 2D to 3D. Right, where now you're using, right, more, I'll say, legacy wafer techniques becoming advanced packaging techniques. And as a result, we're stacking and being able to essentially innovate in 3 dimensions, right, as opposed to 2 dimensions. And as a result of this new use of 2.5 and 3D packaging, we see this ability to bring 1 trillion transistors into a single package by the end of the decade. So against that, for all of the critics that declare we're dead, right, and we think of Intel as the steward of Moore's Law, right, until the periodic table is exhausted, we ain't finished, right? We're going to stay on that journey. Moore's Law is alive and well, and if you want to help it be true to the future, come on down. We're happy to have you, right, if you're good, right? Right? If you're really good, we'll hire you. Sorry, I'm a Stanford grad, so, right, I'm not sure I would have made it if I was at MIT, but anyway, you all are pretty smart too. So we are the stewards. We're going to keep it going at 1 trillion transistors by the end of the decade.
Wonderful. That's a great future ahead of us. So I recently learned something interesting. I learned that the energy consumed in the fabrication of the chips that Apple uses is the single biggest item in Apple's carbon emissions. In fact, the chips that they use every year to build their devices making those chips consumes more energy than all the Apple devices worldwide being used on that year. And in fact, also, more advanced generations of semiconductor technology consume more energy in their making. So what's the path for greening this industry, which is a big concern at this time?
Yeah, and it's super interesting, and Intel has unquestionably been the environmental leader, right, in semiconductors for decades. And this was a huge passion. Our 3 founders, I call them the Trinity of Silicon Valley and the silicon industry. Gordon Moore, Robert Noyce, Andy Grove, and Gordon Moore was particularly passionate on this topic, right? Climate and environmental and so on. So it's deep in the ethos of Intel from our very founding. So today, if you look at, for instance, energy use, we're about 90% green energy today in our fabrication facilities, which is an extraordinary statement. When I was being, giving my Senate testimony to support the CHIPS CHIPS Act, right, passage. I would view it as more of an assault by senators on you if you're doing Senate testimony. All deference to our legal ridden, Senate leaders. But they, one of the senators pointedly asked me, he says, so if we give you CHIPS money, do you commit to, right, being net zero by 2050? And I said, Senator, no. We're going to do it by 2040. Right. Now, of course, most of the other people that were testifying for the Senate had no specific plans yet. But we are well advanced in this area. But to us, it's not just energy and green energy. In that sense, it's also water. Right, and like our Arizona fab, we have a fab in the middle of the desert of Arizona. We're about 92% water recycling, and if we combine that with all the water reclamation projects we do, we're over 100% water, right, for it. It's also things like chlorofluids and other, noxious materials and how we take those out of the manufacturing process as well. And it's just one of these things. You just got to get on it, right, as good engineers, good scientists, good environmentally conscious one by one. But, we stand in stark contrast to the rest of the industry. We are decades ahead of, Samsung's TSMC, in this regard, and something we're quite proud of. So if you want an environmentally conscious chip, you need Intel inside.
Wonderful. So Ann Kelleher, who is the Intel CTO, has said recently that Moore's law is and always has been driven by innovation. And so we know also that there is a deep connection between innovation and manufacturing prowess through the learning curve. The more you make, the better you get at it, the cheaper your products are going to be, the more competitive you will be. And so as manufacturing volume and ability, therefore, manufacturing volume and innovation go hand in hand. And perhaps this is why the industry has consolidated in the last 3 years to essentially 3 companies that are sitting at the leading edge. So if we look forward, what does this mean for the future of semiconductor manufacturing at the leading edge, and what does it mean for Intel?
Yeah, and how many of you believe we're going to have a more digital future? Okay, duh, right? And everything digital runs on semiconductors, right? Just, there is no digital without semiconductors, right, today. And as you think about that digital future, right, and one of the things that, has driven my passions in coming back to the company, right, the CHIPS Act, et cetera, is where do you want that digital future to be built, right? In 1990, 80% of semiconductors were built in US and Europe. Today, 80% of semiconductors are built in Asia. Right, with a huge concentration in Taiwan, one of the most geopolitically unstable areas of the earth, right? And, let me just give you like 3 factoids about Taiwan. One, other than not having any natural resources, not having energy, no energy reserves, right? Sitting on a major fault line, right? And now being essentially tapped out of its talent capacity. They don't have an MIT, right? Locally, they have good schools and so on. It's like, and right, so essentially you have this extraordinary world dependency, right, on a very small area of the planet. This is not good. For the geopolitical stability, the resilience, and the resilience of our supply chains, and this became acutely visible as we went through the COVID crisis. So what do we want to do? Right? It's not like we, deglobalization, that's not the right way to view it. We want balanced, resilient supply chains spread across the world. And that's what we're out to accomplish, with the CHIPS Act and what Intel is, driving quite aggressively. Let's build the fabs where we want them. Geopolitics has been defined by oil over the last 50 years. Technology supply chains is more important for a digital future than oil for the next 50 years. Build them where we want them, and we can build them right here, right at that point. So we've taken a huge agenda to establishing this balanced, resilient view of our technology supply chains. It's not just that we want to, I have nothing against software engineers, but at the end of the day, it runs on hardware. Our digital future runs on semiconductors. And semiconductors is a volume manufacturing game, right? The engineering, the innovation is never done. Right, a fab, is not something you turn on and just pull wafers out, right? You are innovating in that fab every single lot, wafer, telemetry, readout, et cetera, is learnings on defect densities, new material understanding, new defect models, new equipment efficiencies. This is a living, breathing manufacturing organism if you're going to be in semiconductors, right, for it. And this is one of the things that the founders of Intel deeply believed. You can't innovate and not manufacture. Those are inextricable, right, in our industry. And if we're going to be an innovator at the heart and soul of the digital future, we must be a manufacturer at scale. So this is, deep in it, what I'm driving as a company, some might think, there's a thin line in, being a CEO between being bold and crazy. And right now, Wall Street's not sure which of that line I am on, right? Before I became CEO, Intel gave $70 billion to shareholders and put $50 billion into capital. The 5-year plan I have laid out for the company is $150 billion of capital and $20 billion to shareholders. This is very expensive. This is very hard. But these are also great industries for us, great jobs, the most innovative PhDs in material science, all the way down to advanced construction jobs for these facilities. Because these construction sites, a $20 billion fab is an extraordinary statement. It is one of the biggest construction projects on the planet, but it is also one of the smallest, most refined, materials are being produced on Earth. So it's not only the biggest, but also the most precise as well. And that's what we're doing with these projects, is reshoring, rebalancing our manufacturing, leading in the core technology for the digital future, and doing it right in U.S. and Europe. What I believe is essentially the future, right, of the planet rests on what we're doing in building our technology future.
Daniela,
and if that doesn't inspire you, why are you here?
I'm inspired. I'm inspired. I'm inspired by your vision for sustainable manufacturing and for connecting innovation and manufacturing. And I think we're going to need increasingly more of that, because AI is here. AI is revolutionizing the marketplace. With ChatGPT, AI has become democratized. It's in everyone's pockets. But in order for AI to do its magic, it needs the platforms, it needs the computers. So my question is, what is Intel doing for the development of AI hardware, and how do you see that as a competitive advantage?
Yeah, and one of the things, a little bit of my own personal story. I was, I started at Intel so young, right? I went through puberty there, right? I feel, I grew up at the feet of Grosvenor and Noyce and Moore, 30 years with the company. Then I took an 11-year vacation, right? To EMC and VMware, which, by the way, I was outside of Intel almost to the day, the same time Steve Jobs was out of Apple. Right? It's like, okay, it's like the death of the vision. I wanted to be the CEO of Intel. But when I was pushed out of the company 13 years ago, they killed the project that would have changed the shape of AI. Right? I had a project underway. It was called Larrabee at the time, to do high throughput computing in the x86 architecture. They killed it after I left. NVIDIA had unmerited potential in the space of AI hardware, essentially throughput computing versus scalar computing. Nobody put pressure on him. And Jensen, by the way, he's I know him super well, right? He worked super hard at owning throughput computing, primarily for graphics initially, and then he got extraordinarily lucky, right? They didn't even want to support their first AI project, right? And it's just, hey, big flop machines was needed, for these big data sets that they were looking at. So Intel basically did nothing in the space for 15 years. And now as I come back, I have a passion. Okay, we're going to start showing up in that space. And our strategy here is, number one, is democratize AI. Because today you see the collision of high-performance computing AI, for these 100 billion, soon going to be trillion-dollar, parameter models that we're training on that take, 30, 60, 90 days for training. How many of those can you do? Right? It is the ultimate of, like high-performance computing, weather modeling, nuclear simulation, high-end training. You can't afford it, and so on. So what are we going to do? We want to democratize AI. We want to make it available to every application developer, that you can put it under your desk. It's in your laptop. Our next generation client products will have 20 tops, right, in a standard, mediocre, right, PC. Okay, it's 20 tops, right? That was more than, was possible on a high-end supercomputer about 15 years ago. So, democratize and also open up the software stack, right, for industry standards, get away from the proprietary technologies, and we're driving a technology called SYCL, an open standardized parallel C, so that we can eliminate proprietary technologies like CUDA. And, right, we begin to offering our high-end computing chips to compete in that high-end training space as well, build it into our standard Xeon processors to truly make AI available for any and all, because it is the most important active workload today. And, hey, it's evolving like crazy, right? It's like, I helped to create IEEE P854, right, which was the floating point standard at 64 and 80 bits. Okay, now we're talking about FP8? It's like, what, right? Such trivial low-end data types and are, suitable, right? Because instead of big vectors, let's create little things that are guessing, right, at the right answer, and AI is just sort of a probabilistic guess for most things. So, it's changing rapidly, sparse matrices, different algorithmic models, breakthroughs happening, rapidly. And if we think about AI, essentially you look at something like ChatGPT, incredible technology, but it's on the simplest data set, text. Right? We're going to start getting to some hard data sets, right, going forward, which are going to be orders of magnitude more challenging than the ones that we're solving today with AI. So, I think we have at least a decade, probably 2 decades of just sheer innovation in front of us, and all of it's going to need extraordinary amounts of data, extraordinary amounts of networking, and big honking compute. So we're going to build lots of fabs so we can build lots of compute.
So just following up a bit on that, I'm wondering, so do you see AI evolving in terms of building increasingly bigger models, or do you see other aspects of AI taking flight? And what do you think is the role of hardware versus software so that we can achieve your democratization vision?
Yeah, and there's huge activities right now. How do you take these enormous models that are produced by the training and be able to crush them down into something that you can put onto a single node in the server, right, or even into a desktop, right, and be able to compress those models. And I think that's going to continue in this idea of democratizing AI, right? We can't have these super high-end, high-performance computing machines as the only way that you can do model training. We have to bring it down. There's also dramatic innovations going on in, I'll say, just the algorithmic domain of AI, as well as we're going to larger memory spaces with sparser representations as well. And if you view computing as a world of scalar computing versus throughput computing, well, when you get to sparser matrices, it's sort of those worlds are coming more together, right? And you're combining vectors and high throughput matrix structures as well. It's not clear that the algorithmic domains that are dominating AI today will continue to dominate, in the next couple of years of innovation that are going on. And in that, I'll say, if anybody tells me that you can predict what the next major AI breakthrough is, I doubt that you have figured it out, because a lot of this is we're doing, heuristic understanding of different algorithms that have been proved effective, combining them together against certain training data set processes and coming up with tremendous insights, that result from it. And I expect that that's going to be the case for the next decade, for it. And, hey, some of them, hey, maybe you're going to find, the Xeon CPU is the only way that you do that problem. And we're going to be lucky as well. So I would hope so.
That's really
but,
great.
and also just one more point on this is, as these models, they're also now going to start touching on different aspects of computing as well. How do you secure these models?
Yep.
Right? As you're, if you're going to spend, essentially, a billion compute hours creating a model, right? Are you going to give it away, or is it going to be protected? Also, how are you going to do distributed retraining of models, right? Because you may or may not want your medical data, being exposed in the model and the biases associated with that. How are you going to have competing models to make sure that the models themselves weren't trained with biased data? in the first place, right? There's going to be lots of problems that emerge as we start really understanding some of these next algorithmic domains. It's a thrilling time to be a computer scientist, but it's even more thrilling to be a semiconductor manufacturing engineer.
But the two are married. You cannot have one without the other. So let's see. How do you think of the other big players like Google, Microsoft? How do you see your relationship with them? And do you compete with them? Do you collaborate with them?
In many ways, these are big customers of ours, right? And Google, Amazon, Microsoft, Alibaba, these are some of my biggest customers, so I have to like them, right? And most of them have some level of programs that compete with us as well, where they say, I want to go do a TPU because I want to do a TPU. I have engineering, I have innovation going on. And even for those programs, as we become a foundry for companies for the world, I still want to capture their designs on my foundry. So even in that case, I would prefer they use my chips, my designs, but even not, I want them to use my wafers as well. So in many cases, it's like, and this bubbling cauldron of innovation, right, that's going on, it's super hard to decide who's a competitor and who's a collaborator, right, because there is so much going on in this space. And the technology industry has, one is we've thrived on open, right? And we deeply believe in open standard innovations where, we get to stand on the shoulders of the work that has gone before us, something we deeply believe in at that level. But it's also thrived on co-opetition, right? Because it's not clear some days who's going to be your competitor or who's going to be your customer, right, the next day. So this combination of open innovation, combined with co-opetition, right, it's like, I like them all because they might be my biggest customer tomorrow, right, even though I'm competing with them in certain areas today.
So that's amazing. May I ask another
One
question?
more.
Okay, one more. Two more. One more. Okay, so I wanted to ask you about your workforce, about your employees. What does Intel do to ensure that everyone, in some sense, understands AI, understands the power, the transformational power of AI? How do you prepare your workforce for this future where your hardware will be increasingly targeted to AI?
Yeah, and as we think about it, it's always and even hard times, good times, and right now it's a hard time as we've done some reductions in the company. We never stop hiring new college grads, right? It's like the lifeblood of innovation is continue to bring in next generation talent into the company, and we would say that's something super important, because right, these kids don't realize what's possible and not, right? That's sort of the source of innovation. Right? When you get old, you start limiting yourself in your thinking. Oh, we've always done it that way, right? So you keep that source of innovation. A lot of that is driven by these next generation technologies like AI coming into the. Well, why have you do it that way? Have you tried this? Right? You keep that activity. Also we make sure that we keep a very vibrant research community. And Intel Labs is a very active, research community where we're, participating in this bubbling cauldron of innovation very actively, research papers, open source projects, engaging, with research grants. And, by the way, I was actually pretty startled in my briefing coming here. MIT is my #2 research-funded university. Yeah.
Number one.
That's an MIT thing to say. I was pretty startled you were #2, so now you're #1. But we don't hire enough of you, so that's a different problem, right? But part of that is just you're always in the technology industry. What was good yesterday, right, is standard today, is legacy tomorrow. Right, and you just got to be constantly going, through that innovation cycle.
How do you approach reskilling and training to make sure that your workforce is ready for the transformation of tomorrow?
Painfully hard, right? And I just, reskilling, retraining, workforce development, et cetera, and particularly a lot of our jobs, like in our fabs and so on, there aren't good programs anymore. right, in that area. So a lot of it is bring in good raw talent and immediately put them into those settings, hands-on, developing them. But we're also constantly investing in, workforce development for, internally as well as for the future. And when, one of the proudest days of, being the CEO of a turnaround, you have good days. Every CEO has good days and bad days. The CEO of a turnaround, you have more bad days than good days, right, for it. But last year, I had 5 great days. Not good days. I had 5 great days, and one of my great days last year was the Ohio groundbreaking, right? And, when I got to stand on stage next to POTUS, and I said, today, the Rust Belt ends. Today, the Silicon Heartland begins. You could feel the national pride just welling up inside of you. And when we did that, in addition, huge capital investments and everything else that goes into it, but we also announced a $100 million program, $50 million from us, $50 million from NSF, specifically on workforce development, for that manufacturing, location that we were, beginning to get underway. So it's, it's deeply in the careabouts of our company. What are we doing in training, workforce development, and skilling of the future? Something we deeply, deeply believed in. That's been one of the areas that Intel has always differentiated itself.
It's amazing.
Maybe I can add to that and ask you, look 5 years from now and imagine the workforce you truly need. Because those are the people we need to start training right now.
Yep.
Who are they? How are they different? What is unique about them that the previous generations didn't have?
Yeah, one of the things that, we've touched on already, clearly, they're going to view, AI tools and skills, like I would have used a spreadsheet. Right early in my, of course I do that, right? Let's go run an AI model against that. Here's my data sets. That's just going to be like standard, tools of the trade walking in. Another aspect that we desperately, and I think we will uniquely want, is, today in our factories, if you look at the workforce man hours required to produce 1,000 wafer starts a week. Okay. I am not at the level of automation and efficiency as TSMC is today. So I need a class of workers that are going to be able to create the most efficient factories that, with the highest automation, metrology, tool efficiency, et cetera. And a lot of the AI tools are going to be useful for that as well, because my cost of labor is higher than Taiwan or Asia as well. So not only do I need to automate to get to the same number of hours per wafer, but if I'm going to actually be cost effective in the world, I have to be more, because our cost of labor is higher as well. But hey, that's what America has always done, right? Every hard, problem and efficiency, we've come up with new automation and innovation solutions to solve it. So, that's a class of things where if we're going to bring manufacturing back to the U.S., we can't just have it be, equal jobs running, in the U.S. We have to have better jobs using higher automation, more robotics, more, innovation and AI efficiency associated. So another class of the kind of talent that we're going to need, and I need people who are, like loving in the nano, right, MIT location. Those are the kind of folks I need, right? People who love to say, that, it isn't just some ether of software. No, I built something today. Let me show you what came out of our factory today. Let me show you my $250 million lithography machine, and how I've innovated that, how I've printed the finest line that's ever been produced on planet Earth, how I've cantilevered molecules into a, structure that has never been produced before on Earth. That's what I want to do, right? This is like the wood shops of the past, right? This is the microelectronics wood shops of the future, right? And people that are passionate about hardware and doing things that fundamental to science, creating, right, structures and physics and leveraging the periodic table in ways that it's never been leveraged before. Those are the people I need.
Well, we have a lot of those. So we very much look forward to indeed enticing them to join Intel. But if you look at the gap between what's happening in academia and what industry truly needs, sometimes it appears to be a very large gap between us, where we can extrapolate and new science and rethink the way the transistors can be made. With no semiconductors, we might be able to make a switch with a 12-volt subthreshold slope, a 12 millivolts per decade subthreshold slope, right, that is unbelievably good performing. And of course, will not be scaled because it is not fitting necessarily into the model of what has been scaled up to that point. So I'm wondering, is there a way to bridge that gap? Is there a way to bridge the gap between tremendous power and complexity, the most incredibly innovative work that humanity has done in the form of present chips, and the new innovations? We are trying to redesign that old innovation. After all, we tell all our students their job is to change the world, not follow the yesterday's guy.
Yeah. One of the things I'm quite excited about coming out as part of the CHIPS Act was also NSTC, right? Which is the National Semiconductor Technology Center that's also being formed as part of that, right? And the related, what I'll call the secure facility sidecar, right? Defense innovation, so on, right? These fabs, truly they cost $20–30 billion, right? What's the entire budget of the Nano Center?
60 million tools, 10 million a year to run it. Yes.
Yeah, so 60 million versus 30 billion if you're going to build one of these modern super, right, facilities. I mean, the scale, the cost, literally, I have single pieces of lithography equipment that are $250 million, right, for one piece of equipment. And to run a fab, I need about a dozen of those, right, to run a fab at scale. So with that, this gross economic gap between what you can do in academia, even what, with all of the power of the defense and intelligence community, they can't afford their own fab. Can't be done, right, at that level. So how do we bridge those two worlds, right, forward? And I just call it the sidecar. And I want to take my superhighway that I am building, and I want to create a research sidecar and a secure sidecar, that meets all of the unique requirements of, defense, intelligence, et cetera, so the secret handshakes and, the special SCIF facilities and, all of those kind of things that you need to meet their needs, but also create this domain for research innovation as well. Because you cannot possibly afford to put these equipments into a research domain. So how do we create an environment where we can sort of work together? Right, and with NSTC help to form, right, that halfway house, if you would, between, these massive investments for the commercial thoroughfare, right, and being able to open up pathways for, fundamental, innovative research work, that we're able to do together. We're also, we run the university shuttle program, that we started, which is allowing people to design, and it's on Intel 16, so a 16 nanometer, facility. I'm anxious to get that to Intel 3, so a 3 nanometer, process technology. In 2021, we ran about 60 shuttles. In 2022, we ran about 400 shuttles. And my goal would be about an order of magnitude each year so that every university, right, every university class and researcher, can go on to a modern technology node for their research work, for their design work, for their skilling work as well. So that's the vision, that I hope that we bring about, and NSTC and the CHIPS Act are key components, of building, I'll say, these sidecars, right, and that scaling of the shuttle programs.
That's fantastic. It does require us, though, to design for those specific tool sets, as opposed to using our present tools and trying to reinvent the next set of technologies just with them. So imagine we do reinvent it. What other materials besides silicon might find themselves being able to be used in this material, in this very advanced system? So
a little, silicon, right, is like God's gift for humanity, right? This 4-4 structure, very stable, very manufacturable, and you can shove all sorts of other atoms and molecules into it, right? You can stress its, you can stress it, right? You can bend it, you can shove things into, and it's just amazing. And if you look at a silicon chip today, there's amazingly little silicon in it. when you look at the transistors. I mean, you're using, high K metal gates, you're using different materials on it, right? It's essentially the scaffolding that we're building microelectronics on top of, right? And that's why it's so amazing. And that's why I say we're not finished until we've exhausted the periodic table. Right? We're going to find ways to add materials and use the scaffolding that God gave us in the silicon, right? And just keep shoving more materials, on top of it, in it, and bend it. And right now there's like a lot of research going on ferroelectrics. Okay, how do we layer those on top of silicon? Because if I can make it somehow work on top of silicon, I got massive factories I can run it into. I got all these equipments. I got etchers and depositors and lithographics and so on like that. So to some degree, the direct answer to your question is what kind of materials? All of them. Right? Because we want to just keep opening that envelope, right, of the periodic table of innovation and new molecules and discovering new effects. And then if I can put it on top of silicon, and by the way, it's proven to be this extraordinary material, right? I can now make it at scale for the planet. Like we have our quantum program, our quantum dot program. Ours is different than, some are doing them, with supercooling effects, and some are doing them with lasers and so on like that. We're doing ours on top of silicon, right? And part of the reason I believe we will win in producing the first useful quantum computing is because you probably need, let's estimate maybe a 1 million qubit machine, right, to create a useful couple thousand qubits, logical programmable qubits that are stable, error corrected, et cetera. So I don't think any of the other approaches you're ever going to get close to being able to build 1 million qubits. I am confident I can build 1 million qubits because that's what we do, with manufacturing at scale. So I believe we're going to win the quantum race as well. Maybe you don't. Maybe you love one of those other techniques. That's okay. Let the race be gone. But I think by about 2030 we will deliver sustainable quantum computing, right, and deliver quantum supremacy on meaningful algorithms in a substantive way. And I think that's the new. Right, if we talked about the AI collision with HPC, the next supercomputers will be quantum-based, and my thumb in the air is we'll hit that right around 2030, 2031.
So I'll ask my last question, which is, I completely subscribe to everything you just said. Very excited. What do I need to do to help you out? What do universities need to do to assist Intel in reaching this vision?
Well, let me give the flip answer. All of your students that are good need to come to Intel and work for us, and all of your research projects should be aligned with Intel's agenda and everything, right? So, right.
Excellent.
Along that line, what other advice do you have for our students?
Yeah. So now being a little bit more serious in that regard, I do believe that we are in this period of time where we get to decide if we manufacture the future. I am confident that we will invent the future. The question in my mind is, will we manufacture the future? Are we going to be owning the supply chain of manufacturing and delivering this, at scale? Are we going to, are Western countries going to do that? Or are we going to allow that to drift away? And I think this is a moment in time, right, where if we don't act decisively, and that's why, when I had the chance to be on the White House lawn for the CHIPS Act signing this last year, that was another one of my 5 great days, right, at that point. Because that was the most significant piece of industrial policy legislation in the United States since World War II. Right, and if you just think about that, we ain't done industrial policy for 70 years. So one of the things as I would look at MIT is, are you going to help make the vision that the president signed, that Congress passed, are you going to make that vision of not just inventing, but also manufacturing the future true, right? And I would say, and that, to me, that is why I rejoined Intel as CEO. And that, to me, is a cause, a purpose, a vision worth us pursuing together. And obviously, there's, MIT attracts the best of the best. Right? Maybe not as good as Stanford, but anyway. I mean, incredible students, incredible minds. and I would hope that every one of them gets into the nano lab, and falls in love again with building hardware, building silicon at scale, because I want the digital future to be based on the things that we invent, that we manufacture, that we deliver to humanity at scale. And that's a very different trajectory than the one that we have been on as a nation for the last 30 years. Congress never voted to get rid of the semiconductor industry, but the parliaments and congresses of China, Taiwan, and Korea voted to get this industry, right? We just voted to get it back. And I need a whole lot of help to make that happen, and I hope to have your participation in that.
But we have 5 minutes for questions from the audience, if you don't mind.
Sure.
There's a microphone here, if you could please. I think we have a question right over there, John.
Right over there.
Yeah. It's tall.
Hey, wanted to thank you for the University Shuttle program that supported my entire PhD here at MIT, including about a half dozen chips. We've now spun out into a startup company here in Cambridge, and the company is now deciding whether our foundry will be Intel or otherwise. And so,
is there a choice?
Yeah, it's a really important choice and a difficult one. But you talked about the roadmap with University Shuttle and supporting universities, and I was hoping you could comment on your plans for the growing domestic startup community.
Yeah, and obviously my passion for the shuttle program is so that it becomes a passion for the venture program, right? So that if you've done your research, right, on Intel shuttle program, it's just, you just go 2 steps to the right and boom, you're running on us as a foundry for a startup program, and then you go, right, as an early user at scale. I mean, that is the pipeline that I'm off building. Now, hey, we are a early foundry provider, right? And I'll just say, our technologies aren't as mature as they need to be yet. I don't have as rich of a EDA, right, IP, right, ecosystem as yet, but we are extraordinarily committed to build that out over the next several years together. And hey, if we're not good enough yet, help us get there.
More questions? This one there.
I have to stand up. Okay. Do you see a role for biological materials in your industry and in this manufacturing of the future?
Hey, I think there's been lots of crazy ideas for different computing structures over time, and lots of different memory structures, and and when you look at all of those approaches, very few of them have mattered at the end of the day, right? For it, and you've essentially ended up with 3, 4 memory types. You've ended up with a couple of transistor types, that have just dominated everything, right? For it. So, there's a lot of the different approaches that people have talked about, and it's great and wonderful research. I'm skeptical that any of them have the kind of market impact that your basic digital transistor has had, right? And silicon as the core material, that we've built on, and the fundamentals of CMOS, NMP devices, have for the future. It's just proven to be so extraordinarily scalable in that regard, and the kind of benefits that something like a biological computer has been able to demonstrate are comparably modest. Now, obviously, by the comments I gave as well, hey, quantum computing is an entirely different domain, right? At that sense, where you've moved past the digital domain, right? You have such a radical different effect that you're leveraging, potentially is super interesting. So that's one that we're excited about. We're also doing things like neuromorphic computing is another research area for us. But in all of those cases, I'm trying to do it on top of a silicon infrastructure so that I know how to scale it over time. We may not be right, but we're not in doubt.
Okay, a couple more questions. There's one here, one there.
Thank you very much for being here. Was Sematech the right concept?
I'm sorry, was?
Sematech in Austin, Texas.
Sematech.
And what happened to it?
The Sematech is an interesting history because most people would look at Sematech and call it a failure, right, at that point. But I would also argue that it catalyzed the industry, when we were getting our heads handed to us in the US to Japan, right? And fundamentally, we won, right? In that, resurgence of industry. So in some senses, I would call it a huge success because it catalyzed the industry, even though that particular research and collaboration model didn't have the kind of effectiveness of flowing things into the industry as it was intended, right? And in some regards, it ended up almost on a model that it was competing with the industry that it was trying to serve. So, right, as we ponder NSTC, the National Semiconductor Technology Center, I think the Semitech experiences need to be in our minds as we're shaping what this next phase of a structured research model needs to look like for the industry, because I will argue that one was not successful, or certainly not as successful as it would have hoped to be at the time.
All right, final question, John.
I believe in the old days, all the great VCs made their reputations in investing in semiconductors. And nowadays, you ask a deep tech VC, hey, what are you doing? And they say blockchain. And they say, would any of you invest in semiconductors? Oh, no, we would never invest in semiconductors anymore. So how do you get the venture community, if you think they're relevant, to share your brilliant vision?
Yeah, and they're actually, if you look at what venture has done, right, with the, I'll say the maturity of the foundry ecosystem that has largely been around TSMC, right? And obviously I hope to change that, but largely been, there's actually been a somewhat resurgence, right, of venture investing around semiconductors over the last 8-9 years in that regard. And you're certainly seeing that results with some of the networking components, but now some of the AI chips that have emerged, some of the RF sensors, other things like that, that have emerged. So I'll say it's a bit more, but not a vibrant, community around it. So I do think that certainly that the NSTC, if I go back to that again, if you get good solid research underway, venture doesn't go do something, they respond to things, right? And I think if NSTC starts creating things, the venture community will respond to those things appropriately, right? In that sense. And that's why, I have viewed the CHIPS and NSTC, ITC, what we're doing, I view it like this domino that starts a set of other dominoes underway. And when I go, for instance, meet with the ASML head, the lithography EUV equipment head, your next R&D location going to be in Ohio, right? Okay, we're ready to start moving that, and where was my friend up here? Your venture company is going to be on the Intel foundry, right? And that will be a startup that gets funded. You're going to be well funded. I am certain of it, right? Right? As you go forward. To me, it's this. We have to start this period of momentum, and then momentum builds on itself going forward. So, and maybe I'm just crazy optimistic on this, but I think this domino has started. Since the CHIPS Act got underway, we've had 5 major manufacturing facilities announced in the U.S. Samsung, TSMC, Micron, and 2 by Intel that we've done. Wow. It isn't going to rebalance the world, but still, that's more manufacturing investment announcements in the U.S. in the last 2 years than was in the 10 years prior. So I will claim, okay, the domino is starting to move forward. A long, long way to go. None of us should be confused. I've said the moonshot is that we've gone from 80-20 to 20-80 to 50-50 in a decade. And hey, even if we get to 60-40 in a decade, that is extraordinary. We've doubled the manufacturing capacity on the most critical ingredient, right, of the economy and the digital future and every human on the planet, right? Man, what an extraordinary result that would be, if we're able to even get to that level over this period of time. And I think we can.
Mm-hmm. Well, thank you, Pat, for coming to share with us your optimistic outlook for the semiconductor industry. Thank you again, please. Thank you. Fantastic.
Thank you so much.
Thank you so much. Beautiful remarks.
So inspired. So inspired. Let's do a selfie.